Good evening, everyone. We are going to commence another webinar conducted by Institute of Physics Sri Lanka. Thank you for being here today also. We have been organizing this monthly webinar series to promote physics and its applications and where the public on hot key topics related to physics. So today webinar, we have invited young postdoctoral researcher, who is Dr. Madhuranga Thilakasiri from Arizona State University. His research is on high energy physics. Today he will present on sneak peek into vector-like quarks. On behalf of IPSL, I would like to warmly welcome Dr. Madhuranga Thilakasiri. Thank you for accepting our invitation today. Before I start the presentation, I would like to call upon Dr. Chathuri Nupiarachi, co-editor of IPSL, to introduce today's resource person. Thank you very much, and over to Dr. Chathuri.
Thank you so much, sir, and it's my honor and privilege to give a brief bio about our resource person today. Dr. Madhuranga is from Anuradhapura and he has completed his school studies from Anuradhapura Deepani Mahavidyalaya and Anuradhapura Central College. He started his undergraduate studies at the University of Sri Jayawardhanapura and graduated with a first-class honors specializing physics in 2010. He briefly worked as a research scientist at the Industrial Metrology Laboratory of ITI before he started his graduate studies at Oklahoma State University, OSU, back in 2013. As a graduate student of Oklahoma State University and the Atlas detector of CERN, he worked on experimental high-energy physics, and his dissertation work was on beyond standard model BSM physics with the focus on vector-like quarks, VLQ, and it was a collaborative work with the experimental particle physics group at the University of Toronto, Canada. He contributed the analysis by developing an analysis and data visualizing scripts in search for decaying of single VLQ top quarks into all hadronic final states of the Atlas detector. His analysis is currently in the finalization steps and is expected to be published soon. He also contributed to the upcoming massive upgrade to the Large Hadron Collider, LHC, by deriving efficiencies and uncertainties for the flavor tagging in the proposed new inner tracker of the Atlas detector and determined the same for the pixel option proposed for the ITK. He developed both new and modified standard machine learning tools to determine the aforementioned activities. He graduated from Oklahoma State University back in 2020 and joined the Biodesign Institute at Arizona State University as a postdoctoral research scholar. As a bioinformatician, he is currently involved in producing analytic scripts for gene sequencing and developing and training machine learning algorithms to recognize specific gene locations in human genome that are sensitive to various environmental exposures. So dear ladies and gentlemen, hope you are in for a lovely treat, and Dr. Madhuranga, this digital platform is yours right now.
Awesome, thank you. Let me first thank Professor Shanta Gamage sir for inviting me for this great opportunity. I'm really privileged to give a webinar at this prestigious institution of Physics Sri Lanka. And also thank you very much, Dr. Chathuri, for the my biography. You did an awesome job. So let me quickly share my slides. Can you guys see my slides now?
Yes, you can. Yeah.
Awesome.
Yeah.
Okay. So good evening, ladies and gentlemen. I'm going to talk about a brief introduction about the new hot topics in high energy physics, which are known as vector-like quarks. So I will first lay out a brief introduction to the standard model, the model that we are currently using to understand our nature. Then I will give a very brief introduction to the place we are gathering this information for our analysis, the Large Hadron Collider and the Atlas detector, which I was a member of. And then I will get into the vector-like quarks, just lay out a very brief introduction on what are these vector-like quarks. And then I will also provide a very brief introduction to the VLQ analysis I was involved in. And then finally, I will summarize what we have discussed so far. So to begin with, the standard model is the model we are currently using to understand the nature around ourselves. So the standard model is comprised with 3 generations of particles. You can see this is generation 1, 2, 3. And then we have a bunch of force carrier particles. And then finally in 2012, the Higgs boson was included because they experimentally verified it. So basically, this model is going to explain us like how the matter is made out of. Then if you want to go in further and see how the matter is interacting with each other, this is the model currently we are using. So if you have taken a course in high energy physics during your undergrad studies, you can remember that there are 4 fundamental forces, literally known as strong, weak, electromagnetic, and gravitational. 3 out of 4, except for the gravitation, all the other 3 are included into this. So basically, it's a very elaborate framework to explain what is going around us. So as you know that these fundamental particles, especially these quarks, leptons do exist by themselves and the gauge bosons do exist by themselves, but these quarks are very tiny particles so that they cannot be found as an individual particle in nature. Rather, they will always bound to each other and make particles out of them. So one of the best examples is a proton, which is made out of 2 up quarks and 1 down quarks. And the other one is the neutron, which is made out of 1 up quark and 2 down quarks. Likewise, they combine together to form subatomic level particles. Then, based on how these particles are combining to each other, we can distinct them either as fermions or bosons. So the main criteria to define particles either as fermions or boson is based on their isospin. So if they have isospin of half or multiples of half, like 2/3, 5/2, something like that, we call them as fermions. If they have integer spins, we call them as bosons. Then comes the composite particles. That means they are comprised with many subatomic particles. We call them as baryons or mesons. So baryons are formed out of combining 3 quarks. Like I mentioned before, the proton is made out of U, and D, up, and down. And then for mesons like pion, it could be U, D bar. That means it's made out of 1 quark and 1 anti-quark combined to each other. So I'll be talking about these hadrons in later of my presentation. So hadrons basically are could be mesons or baryons like protons, neutrons, even quarks. These are going to be really useful in our main analysis related to beyond standard model or even the studies involved in the standard model. So we necessarily need to talk about the device that we are using to generate all this data for our analysis, which is the Large Hadron Collider. So this is the most powerful particle collider or even the machine that ever made by humans. It has a really huge circumference around like 27 kilometers, which is spreading across the France and Switzerland border. And then it is accelerating 2 beams of protons in circular pattern, so that at 4 different locations where the detectors are kept at, they are going to make these 2 proton beams to collide head on. So they will collide like this, and that collision is going to make out of lots of particles. So because of the energy each beam is accelerated at, currently can accelerate the beams up to like individual beam up to like 6.5 tera electron volt. So when they collide head on, they're going to produce a center of mass energy of 13 tera electron volt. So to the particle level energy, 13 tera electron volt is a really huge amount of energy. So they're going to do crazy stuff. They're going to make very heavy particles that could have been at the very beginning of our universe. So people are so fonded about the collisions and the outcoming out of them. So Atlas is one of such detector kept at these 4 locations, and it's going to be even more interesting in the coming years because currently it is going in a very aggressive update so that it will be able to collect more data at the same amount of energy. It's going to collect more data by 2024. So we might be able to sometimes, who knows, find these vector-like quarks in the coming years because compared to the data what we used in our analysis, the proposed is like tenfold. So that's really, really interesting to see what will happen in future. Then the detector I was involved in was the Atlas detector, which is one of the 4 detectors at the Large Hadron Collider complex. So to give a brief introduction to it, it comprises with 3 major components. At the very innermost position of the detector is the inner detector. This is used to reconstruct the trajectories of the charged particles. So as I said, when the particle beams are colliding each other, out of those 2 beams, quite a lot of particles can start to come out. And we have to then trace them back to see what was the origin of what we are searching for. Like for an example, let's say we are looking for a vector-like quark. Because it's a very heavy particle, it quickly decays and then decays into variety of daughter particles. So if we can track them back, we can find where was the origin, and it's also going to give us where it is starting from. Then the calorimetric system is going to measure the deposited energies of the charged particles and the hadrons like electrons, photons, and other hadrons. And then muons usually passes through all these inner detector and calorimetric system and then detected at the muon spectrometer. So as I said, because this is producing a huge amount of data about the particles coming out from the collision of the beams, we have to have some kind of a system to keep worthy events and to remove unnecessary events, to get rid of the background noises. So it uses a 2-level filtering system. One is based on hardware, the other one is based on software. So this is like a cross section of the Atlas detector. So as I said, the inner tracker is going to detect the particles coming out from the collision point. So this is the beam line where the collisions take place. Then the electromagnetic calorimeter is going to deposit energies of the charged particles. Then the hadrons will deposit their energies at the hadronic calorimeter. And finally, the muon spectrometers will detect the muons coming out from these kind of collisions. So this is the background, I would say, how we are gathering data for variety of analysis. As I mentioned before, it could be analysis on standard model physics or on beyond standard model physics. We are using this detector, and as I said, these are now under a very aggressive upgrade process. So there'll be a lot of stuff to analyze in the coming years. Now let's get into our topic for today, the vector-like quarks. So like I mentioned before, the model work or the framework we have right now to understand our nature is the standard model. So standard model had a vacuum until 2012 because people have predicted about the existence of this particle called the Higgs boson, which is supposed to give the masses to the other standard models. But the problem is when we have to go beyond the energies of the standard model then start to have limitations to explain what's going out there. Like for an example, why the Higgs boson mass is quite less heavier than some of the standard model particles. For an example, the heaviest generation of particles in the standard models are the top and bottom. The top is around like 175 giga electron volt, while the Higgs boson found to be experimentally verified as 125 giga electron volt. So such an so it's actually brought a question like why it is less severe than even one of the standard model particles. So likewise, explaining such stuff, yes, standard model have some limitations. So that is driving people to test out many new theories like the supersymmetry or like extension to the existing standard model like the beyond standard model theories. So I won't be talking about the supersymmetry today. My focus is only about the vector-like quarks. So vector-like quarks is coming, or rather are coming as an extension to the standard model, so that they are proposing a new fourth generation heavier, even heavier quark than the third generation quarks like top and bottom. The main properties what these vector-like quarks going to have are they're going to have spin half, and they have fractional charges, and they can exist in the nature. They're singlets, so that means like one entity, or they can be there as a coupled entity, like doublets or triplets, based on how they are out there. So these singlets or doublets or triplets are proposed by different theories. So altogether, they can be existing as singlets, doublets, or triplets. Then the other interesting thing is that these vector-like quarks, these heavy vector-like quarks, are coupling to the third generation standard model particles. So you can see here, for an example, if we have this top, this is the vector-like top, and this is the vector-like bottom. They are being named as top and bottom is because they quite behave and looks like the standard model top and bottom. So the vector-like quark can decay into a standard model top or standard model B via weak interactions. So now let's see why these vector-like quarks or these heavier quarks getting this name vector-like. So as I said, when the particles are interacting each other in the standard model, you might have heard that the standard model is a left-handed theory, which means basically the handedness in the particle physics is coming based on the isospin and the momentum of the particle. Let's say if the isospin and the momentum of the particle, if both of them are in the same direction, we call them as right-handed particles. And if the isospin of the particle and the momentum in the opposite directions, then we call them as the left-handed particles. So the formulation of the standard model is a left-handed model, so that for an example, if we take the charge current coming when standard model particles are interacting with each other using the weak interaction, it do so by protecting this vector-like component and axial vector-like component. So these are defining how the standard model framework is laid out. So the standard model particles are therefore expected to protect this vector and axial vector property. And because the standard model is left-handed theory, we do not see right-handed charge currents in nature when standard model particles are interacting with each other using the weak interaction. So when it comes to the vector-like quark, they are quite behaving different, because by the way, how these new beyond standard model theories are predicting the existence of these particles, they have defined the vector-like quarks to behave without any preference for the chirality. So in the vector-like, in the standard model particles, it's very specific. It's only interact using the vector and axial vector components. So it's only interact with the left-handed particles. But the theory is developing these vector-like quarks, suggesting that it has no preference about the chirality. So it only has a vector component, and that's why these heavy new quarks are suggested as the vector-like quarks. As I mentioned before, uh, when it comes to the standard model particles, they do get their masses from the Higgs coupling, or when it interacts with the Higgs field. But the vector-like quarks, because has no handed preference, they do not need to interact with the Higgs to get their masses, and therefore these vector-like quarks can be used to explain why the Higgs mass is less heavier than they expected. So the main reason is the quadratic divergences we are seeing coming from the quantum interactions in the Higgs mass being observed. Vector-like quarks can step into that and explain. So such proposed beyond standard models are like little Higgs and composite Higgs. So now let's see how this kind of vector-like quarks can be produced at the Large Hadron Collider. So they can be produced in two distinctive ways. One is being the single production channel, the other one is known as the pair production channel. So which means when we collide those proton beams, these vector-like quarks either can be produced as a single entity, or they can be produced as a pair. So when we consider the mass of these producing vector-like quarks, the single production channel is favored. If you look into the plot in the right extreme hand, the blue and the green are for the single produced particles, and you can see at heavier mass of the quark, they have a higher cross section of happening that compared to the black line and the dashed black line, which is representing the pair production. So people prefer more to analyze about the single production at the Large Hadron Collider because they have a high chance to have a good cross section at higher masses for the particle. The other one is being, as I mentioned before, the particle proton beams are colliding at each other at a 13 tera electron volt. So if the vector-like quark is being produced as a single, it has a good chance to carry a good mass so that we can detect it compared for a pair of them being produced, because they have to then share a large fraction of that 13 tera electron volt. So they might not have a good mass to detect. So that's why people have a high preference to choose the single production channel for the analysis, which we also did in our study too. So this is these two plots are showing how the vector-like top on the left-hand side and the vector-like bottom on the right-hand side are decaying into various standard model third generation particles. So the analysis we were interested is represented in this solid green line, which the vector-like T quarks goes into a Higgs boson and a standard model top. Now let's get into the study I was involved in. So as I mentioned before, the single production channel is what is favored among many people, because if such a particle is being created during the proton-proton beam collision, this vector-like quark has a good chance to occur and have a good mass that can be leading to its decays and then we can look into the decay products and trace them back to find the particle itself. So as I said, the word hadron is really important here because in our analysis, we were looking at a final state like this, which comprise only the hadrons. So there is a good chance that leptons can, like electrons or muons or tau particles can be there too. And people do also study about them because electrons actually provide a good chance to trace back because they deposit a quite amount of energy at the electromagnetic detector, at the Atlas detector. But why we were interested to see a final state with all hadronic, because when Higgs is actually decaying, it has a high preference to decay into a two bottom quarks. So if we can accurately recognize these bottom quarks, or I will later explain like jets, we have a good chance to get back to the Higgs, and then we can have a good chance to get back to the vector-like top. So therefore, the hadronic channel we are looking at is Higgs goes into a 2Bs, and then the standard model top decays into a boson and a B. The jets I'm explaining here is like when particles are coming out from this kind of a junction, they can be highly energetic, so they come as a spray. So if you observe when you're spraying a fragrance to yourself, if you just spray it and observe, you can see that it goes like a cone shape out from the nozzle. So it's kind of a similar scenario when the particles are coming out this kind of junction or a node. They comes like a collection of particles goes like a spray. So a common term in high energy physics to explain such a spray or a collimated outcome of such particles known as a jet. So we are looking at large radius. This R is standing for radius. And we say it is boosted because this large radius jet can comprise smaller jets inside of it. And those jets are very closer to each other. So being those small jets are closer to each other, it's called boosted. And the other one is being back to back because this vector-like quark is heavy. It's usually the vector-like quarks are defined to be in the tera-electron volt level. So let me step back. The standard model, the heaviest of the standard model particles are the top quark, which is around 175 GeV, but the vector-like quarks, like top or bottom, they are in the tera-electron scale. So they're really heavy, which means they're very energetic. They also carry a momentum with themselves. So when they decay to each other, they decay pretty much back to back. So if you take the frame of reference, if the top quark like this, because it is very highly energetic, the resulting daughter particles can go back to back. So how did we selected events for our analysis was we rejected any leptons from the final state. As I mentioned before, it's because of our preference to see only the hadronic particles at the end of the decay process. Then this anti-KT is a algorithm people have developed to recognize these large R jets coming out at the decay process. Then, as I said, there can be two jets, right? Because the particles were decaying back to back, because these two can go back to back. So we demanded that any of them could be the leading jet, the other one they can be known as second leading jet. We demanded them to be greater than 500 and 350 GeV so that we can see if there is an existing top vector-like quark out there. We can get back to its original mass in the tera-electron level. Then we demanded that these particles need to be coming out of detectors from the center of detector. This data is known as the pseudo rapidity, which tells us how far as an angle did these jets occur or these particle decays are seen. So we demanded that it is less than 2, which means those particles can be detected so close to the center of the detector, again, provides us a good chance to observe such a particle. Then we also made sure that this jet has a mass window of 100 to 225 GeV so that we can see really what's going on there. So this is what I was calling about the larger jets and the smaller jets. So this is not necessarily relevant for our analysis, but these can be recognized as the smaller jets, and you can see here when they get so close to each other, they can be enclosed by another large cone. So this large cone is the large radius jet, and the enclosed two smaller cones are the smaller jets. So we also made sure that they are highly energetic too, and they are also coming closer to the center of the detector. So we have a good chance to observe these. Then we had the challenge of tagging these jets. So we can now observe jets, and then our target is to tag them. The reason is that we need to correctly recognize these bees are actually coming from the decaying Higgs, because the detector is detecting a plethora of particles being produced at the collision of the proton-proton beams. We need to make sure that we are looking at the right stuff. So we therefore do this process called jet tagging. Means we are recognizing them correctly as the decay product of what we are looking for. So when it comes to our analysis, these tools were already developed by the Atlas group. So our collaborative group at the University of Toronto carried out these studies, where they used a deep neural network to tag the top jets, that means jets coming out of this top. And then they used a explicit mass window because the top mass is around 175. They provided a window so that we can first detect the top jet coming from the top, and then we can fine tune them to properly recognize this top is actually coming from the decay of the vector-like top. It's so that it's not being confused with some other top produced during the particle collisions, particle beam collision. Then for the Higgs tagging, we used a mass cut, and we also provided a window 100 to 40 because 140 because the Higgs mass is around 125 GeV, and we also made sure that this tau 21 is saying that if we have two jets within that Higgs jet, these two Bs, how closer they are, and we also provided a cutting point to select after this, it is actually coming as two Bs. So this working point we set was at 70%. So at 70%, we can surely say it is coming as highly closer to jets, two smaller jets from B and B bar. And for this, we didn't use any B tagging. We didn't tag them as Bs. We only worried about if the two jets are coming closer, that's enough for us. Then for these Bs, to identify them separately, we use the another neural network developed by the Atlas group known as the MV2C10. And we use the 70% working point, which means at 70%, with a 70% sure we can say these are coming as these are B jets, so we can tag them as B tag jets. Before I continue, I'm sorry, I was going so quickly. Do you have any questions?
So I think it's better pursue.
Okay. Okay, sir. Then I will continue.
Yeah.
Okay.
Continue and.
Awesome. Awesome. So now comes the interesting part where we are defining the signal and background regions so that we can conduct our analysis. So the signal regions, which I'm going to later show, are supposed to contain two of these. So one is being the leading jet, we can say the leading jet, or it could also be the second leading jet. We have no preference over that, but one of these jets need to be a large radius jet that has one top tag and one B tag subject in it. The other one should have one Higgs tag with two or more B jets. So you can see there could be more Bs in the production, in the decay. So we demanded if it is one Higgs tag, if that jet is one Higgs tag, it should contain two or more jets. Then we add the four momenta, which is the time component and the XYZ components of the jets to get the final state candidate of our searching vector-like Quark top. Then we use the TT bar normalization region. This is mainly for our backgrounds analysis because, as I said, in our subject of interest, the vector like T, in this case is decaying to a standard model top. So we need to have a good mechanism to filter out these tops out of background T, which means when the proton beams are colliding, they can also produce TT bar or single top, likewise many standard model top related jets. So we have to have a good understanding that these T's are coming from our analysis, these T's are coming from the background. Then we also had another set of region defined as validation regions. This is quite resembling to signal regions because of these requirements. One of these requirements might be there in the regions, but those regions are excessively dominated by the background events. So we use these regions into our analysis so that we can optimize our analysis framework and use such optimizations later on to conduct our study. So this is how we defined our analysis regions. So regions in color red represent the signal region. So if you look into the x-axis, it says the leading jet, and the y-axis, the second leading jet, which means those two back-to-back jets coming out from the decay of the vector peacock. You can see, as I mentioned, for an example, if you look into the region 86, the leading jet has one Higgs tag, and it also have two or more B jets. And then if you look into the corresponding y-axis, the second leading jet is therefore has one top and one B. Likewise, we defined the signal regions to contain the decay products of our candidate vector like TCOC. The green are for the TT bar normalization. You can see, for an example, region 66, it has one top here in the second leading jet, as well as one top here on the leading jet. Likewise, it contains the tops, and then the validation regions quite look like the signal region. As I mentioned, see, if you look into subleading jet, it has one Higgs with two or more B jets, and the leading jet has one T only. So it's not precisely the signal region, but it quite looks like the signal region, which we can use, as I said, for our optimization processes. So how we approached for the analysis is that we, for the background studies, not only for the background study, for collectively for the whole analysis, the data Atlas detector collected during the period of 2015 to 2018 were used. And then when it is coming to the background, multi-jet, that means it could be containing particle jets coming like light jets, which means like comprising of very lighter quark jets up and down and their related particles. Likewise, there could be, as I said, plethora of events occur during the collision, right? So this multi-jet background was estimated using the data themselves. And then for the TT bar events, whatever we observed in these TT bar regions, we use those number of events to estimate what's going to be the background. So as I said, there could be other sources generating top quarks. One of such is single top, which means the top quark itself, because it's heavy, can occur as a jet. And those things were estimated by using Monte Carlo simulations. And for the signal, uh, uh, since when I was at the stage of graduating, we were at the stage of optimization the framework. So we didn't really use the actual signal in data. Rather, we used some simulated data. And therefore, this scenario is known in high-energy physics as the signal region kept blinded. And since we're using simulated signal, we had different coupling ratios that define like how the vector-like quark is coupling to the third generation standard model particles. We simulated a few different samples with different coupling values, and then we try to see how the upper limits of the signal cross-section can be seen at with a 95 confidence interval. So to look into the results of our analysis, as I said, we looked at simulated data, using simulated data with 3 different coupling values to see what is the upper limit of the cross-section of our candidate process, T2 Higgs and top. So as I said, because we were in the optimization study, we kept the signal regions blinded. So there's supposed to be a solid back line that shows the observed upper limit. And it's not here because we kept the region blinded at that moment. The red line shows the theoretical cross-section defined. So for lower coupling values, we observed the expected value was quite higher than the theoretical. And this yellow band is showing +1 and minus standard deviation from the expected line. Green is for the +-2 standard deviation. But when the coupling constant get higher, we observe that the expectation line is now crossing the theoretical line. So basically, if any expected line is above, it should be a black line actually showing the observed value. If it is above the expected line is above the solid line, black line, which means that cross section is ruled out. So uh, unfortunately, when I was graduating, we didn't unblinded the analysis. So these are the results we had when I was at the graduation stage. So the conclusions we made, we studied a vector-like T decaying into whole hadronic final state. Our analysis was at a blinded stage, so we used simulated data for optimizations. And then we observed that when the coupling constant, that means when the VLQ top is coupling to standard model third generation particles, the cross section get higher when the coupling is increasing. And before I come to this meeting, I had a meeting with my advisor, and he said that it's now at the final peer reviewing stage, and they are now waiting for the green light from the editor board for the publication. So to summarize our talk for today, the standard model provides a very good framework to understand how nature behaves at very lower levels of energies, like in bigger electron energies. But when things are going at higher energies, standard model have limitations, so new frameworks or extension of the standard model are required to which means it's going to open new frontiers to explore new physics. VLQs are proposed in such extensions to the standard model to answer why things are going weird in high energies. And the analysis I was involved in is now pretty much ready for the publication. So if there are any students participating for today's webinar, guys, there's new physics awaiting for you. Go ahead and enjoy in exploring them. Thank you.
Thank you very much, Dr. Madhuranga. It's very
Thank you, sir.
interesting and it's impressive work. If anyone would like to ask any questions, please feel free to ask.
I might be a little rusty, but I'll try my best to answer your question.
Yeah. So very basic question, what is the size of dimensions of that Atlas detector is size?
Yes, sir. So if you see these two tiny people, that's an average human.
Really?
So really, really huge. Like these are the muon detectors. So from top to bottom, it's like 25 meters. And it has a length of pretty much 44 meters. So this detector is extremely huge.
Yeah.
We have a sister detector too called the CMS. It uses a different mechanism to recognize particles. It's more hardware-based. So they have such differences so that if we are looking for this kind of a vector-like Quarks signal, we have two different approaches to see it. If Atlas is missing, CMS might see it, or vice versa.
Any questions? You mean that the coupling constant is the key parameter when we model?
Yes, sir. Exactly, sir. So what's actually the reason behind is there's a two distinction again difference between the single production and the pair production is that single production is model dependent. Like if we are defining this model, the coupling constant, that might not be the case for another case. So it's model dependent. That's one of the con for single production. For pair production, it doesn't really depending on the model because it produces as a pair, right? So when it comes to the pair production, it's more easy to observe. So some people choose this because they don't have to depend heavily on the model itself. But again, the pros for the single production is that it is possible to see if there is a mass at a very high mass level. So because all the beyond standard models are predicting this is to be in tera electron volt, we have a good chance to detect such one if we're looking at the single production channel.
Understood. Thank you. Any questions? Any other questions?
You can like ask any question like.
Yeah, so.
And so much computational stuff going on. So I highly encourage if students are joining today, Please pay good attention for your programming skills and like try to be really good at Python and especially C++ because these analyses use heavy amount of programming. And whatever the field you will be doing after even your graduation too, it's going to be a life skill for you.
So what's the difference between a super semester and vector-like? So you mentioned about the super semester.
Yes, sir. So the supersymmetry is suggesting something like a seesaw model, which means every standard model particle has a super, that means larger, like a mirror image in another frontier. So the main reason, sir, is that the mass of the Higgs itself. As I said, the mass of the Higgs was measured or observed around 125 GeV. But there are standard model particles like the top quark, which is around 175. So the particle or the field that is supposed to give the mass to the other particle was expected to be much heavier, right? If it can decay into these particles, but it was less heavier. So one reason is that the Higgs field. Now, for an example, if you look into an electron or any other particle, if we define a field for that, like a quantum field, the particle itself is the excitation of that field itself. So usually for the other particles, the vacuum or the zero level, null level, it's just zero. Energy, there's no energy. It's just an excitation of that field itself. But for the Higgs, it is not like that. The vacuum also has an energy level. So the problem is when Higgs interact with itself, that's how Higgs boson gets its mass, or any particle interacts with the Higgs field. The Higgs mass is going to have a lot of contributions from such quantum interactions within itself, within other standard model particles, likewise. So when we try to understand this, there's a huge corrections, quantum mechanics corrections coming to the mass of the Higgs, which also need to be corrected by some other energy scales. That's what I said. The Higgs mass is supposed to be really heavy, but we observe something really tiny, which means those corrections need to be balanced by another set of new physics. That's why we are saying there are new physics. So that new physics can be observed either using supersymmetry, which based on like defining new set of three-generation particles to counter this difference between the quantum correction terms, so that when they counter each other, we observe the mass of the Higgs around 125. The other approach is proposing a set of heavy quarks, so they can decay into Higgs, and then Higgs has a lesser mass, and explain why actually its mass is quite less than we expect.
Right. Thank you. Any questions? So if no question, it's very nice work, and thank you very much for giving very interesting presentation. And thank you very much, Dr. Madhuranga Thilakasiri. And I would like to invite our co-editor of IPSL, Dr. Chathuri Nupearachi, to give a vote of thanks to this. Over to Dr.
Thank you so much, sir. It's my pleasure to give the vote of thanks today, as two of our secretaries are unavailable. And first of all, I would like to thank Dr. Madhuranga Thilakasiri for his honorable participation as a resource person for our November webinar. And thank you so much, dear participants. And we will see you in another very informative webinar back in December. And take care, be safe. Have a nice day, everyone.
Take care, guys.
Thank you very much. Thanks all.
Thank you very much, sir.
Thanks.